So we applied what we learned about the dimension theory of Noetherian local rings to understand polynomial ring over a field, and we concluded that the dimension of the polynomial ring last time, that the dimension of a polynomial ring in n variables is n, where k is a field. Okay. This says that there exists a chain of prime ideals. Recall we are in a domain, so 0 is a prime, Pn, and we know one choice, which is just the variables. So we could take this to be xi and here to be x1 through up to xi, this one to be x1 and then x1 through xi, and then all the variables here. Okay. So there exists such a chain of prime ideals, and every chain of primes has length less than or equal to n. Okay. But in fact, one can prove, so fact, meaning this is a result that I am going to state, and I will only sketch a proof, and not sketch a proof in the sense that I leave the details as exercise to you. The details themselves require proofs and theorems which we could have proved, but we have not. Okay, so take this just as a general discussion. Okay, so in fact, every saturated chain of primes in K x1 through xn, again K is a field, okay, has length n. Okay. What does saturated mean here? So this means that for such a chain, P0 inside P1 Pn, one cannot insert a prime between successive stages, okay, between Pi and Pi plus 1 for any I. Okay. That's what we mean by saturated. In other words, we cannot add more elements into the chain. So it has to start from the 0 prime ideal and end at a maximal ideal, and no gaps in between, in the sense that okay. So every saturated prime ideal has length n. Okay, so this is what theorem. This is a property about polynomial rings over fields. Okay, and we will not be able to prove this because its proof uses two other theorems. So let me just briefly sketch what is behind the proof. It's a good thing to know. Even if we have not seen the proofs of those results, it's a good thing to know that those results exist. Okay? So the first step is, okay, we need a stronger version stronger Noether normalization lemma. Okay, what do we need? Okay, so we need the following, which is that, okay, so given a chain of ideals, not necessarily prime ideals, I0 inside I1 inside some Im, not necessarily maximal or not necessarily saturated. Okay, so there exists algebraically independent Z1 through Zn inside R. R is a polynomial ring in n variables. Okay, such that R is finite over the usual statement about Noether normalization. So let's call that ring A, K adjoint Z1 through Zn, okay, and Ij contracted to A is of the form Z1 through Zhj for some integer hj. Okay, so this is for all j. For all j, for all ideals in that family, okay, when we contract it to this subring, we get the ideal generated by these initial sum number of variables z1, z1, z2, z1, z2, z3. It need not go one step at a time. Okay. It can go. I mean, this h of j plus 1 need not be h of j plus 1. Okay. So it is just some function. Okay. The way we have defined it, it is clearly weakly increasing, because ij plus 1 contains this, so the contraction also has to contain. Okay. But this is something that we need. So this stronger version of Noether normalization is the one that is one step of the proof of this theorem. Okay. So this thing is proved in two sources I know. So for a proof of this version of Noether normalization lemma, it is proved in Serre local algebra. Okay. And it's also proved in Eisenberg's book, commutative algebra, the one that we had mentioned in the beginning, commutative algebra with a view towards algebraic geometry. Okay, so it's a proof of that statement is given in at least these two books. Okay, so that so we need to use this version. Okay, so let's assume that theorem. So so then what do we know? Okay, so let's look at this statement. It says that every chain of prime ideals in this has length n. Okay, so now we can think of it in another way, which is the way we will try to use now. So let P be a prime ideal in R. Okay, so let's just draw a picture. This is a 0 prime ideal. P contains that, and P contains some maximal ideal M. Okay, so this is containment. So I have drawn increasing to say larger and larger ideals. Okay, so this containment like this. Now, what we are trying to sketch is a proof of the fact that every chain from M 0 to M. So this is a maximal ideal. This is just prime. Every chain from 0 to M has the same length n. Okay, that's what we're trying to prove. Suppose it is true, then it would say that every chain from 0 to P followed by a chain from P to M, the length would be equal to n. Okay, for every chain, because if there is some chain which is short here, then you append that chain to the side, and then you'll get a shorter chain which is smaller than of length less than n. Or the same thing here, if there is a chain between P and M which is shorter, okay, then first start a chain from 0 to p and then use the shorter one here, we will get something which is less than n. Okay? Yeah. So the conclusion of this thing is that every chain from 0 to p has the same length and every chain from p to m has the same length. Okay? In other words, the conclusion is that okay, so every chain, so let's write this. Okay, so I'll write here. Every chain from 0 to p has the same length. Okay. Similarly, from p to m. Okay. So these two are okay. Now this is true for every p. Okay. So one observation that we get immediately is that height of p, which is the length of the longest chain from 0 to p, they are all the same length. Dimension of p, which is the length of the longest chain from p to a maximal ideal containing p, but they are okay, but they are all the same length because the total length is n. So dimension of R mod p equals n. So a consequence of this thing that we are trying to prove is that this is true for a p. Now if this is true for every p, then it would say that every chain from 0 to maximal ideal will have the same length, because suppose you take a shorter chain, then take a prime in between, okay, its height okay, so this you have to go up one step at a time. Okay, so the other direction, height of p plus dimension of R mod p equals n. Okay, so R is that polynomial ring for all p, will imply that every chain from 0 to a maximal ideal, every saturated chain maximal ideal has the same length. N. So this statement here is equivalent to what we are trying to prove, so we will prove this statement. Okay. We will also see it in a slightly different way after we finish the sketch of this proof. Okay. So it is this equivalent version that we are trying to prove. Okay. So now let's apply. So let P be in spec R. Okay. Now for the chain 0 to P to maximal ideal, okay, for this find a Newton normalization okay, A, which is some k z1 through zn inside R, okay, such that P contracted to A is some z1 through some zc, okay, or maybe zh. There's only one, so we can just call it zh. And M contracted to R is all of these z1. So this is ideal generated in A, zn A. And 0 contracted to A is anyway 0. So we get such a relation. Okay. Now since A to R is integral, finite, okay, so this one has height. Okay, notice that this one is easy to determine. This one has height h in A. Okay. R is integral. Okay. Yeah, or maybe we don't need equality here, just greater than or equal to h in A, because clearly there's a chain of primes 1 z1, z1 z2, z1 z2 z3 going that way up to zh. So there's at least this ideal has height at least h. Okay. R is integral, so which means that yeah, actually we don't particularly caveats. Okay, height of P is less than or equal to height of Z1 through ZH inside A. Okay. So this we proved when we discussed integral extensions. Okay. So if P contracts to A to R is integral, P contracts to A, then height of P is less than or equal to height of the contraction. Okay. So this we proved. Okay. So now what is the picture? We have a P here and we have Z1 through ZH here inside A. So this is inside R. Okay. And A to R is an integral. Okay, this contracts here. We want to show that height of P is at least H. Okay. How would we prove that? Okay, so this is, okay. Let's look at a chain of primes here. So this one contains Z1 up to ZH minus 1 and so on, contains Z1 and contains 0. These are all strict containments. Okay. We have seen the going up theorem, which said that if an ideal in the extension ring contract, okay, let's draw the going up theorem. Okay, so let's use slightly different notation. Let's call the rings S1 and S2. Just okay. So this is S1 and S2 integral extension of, okay, and we have some P2 inside P1, okay, primes here, some Q1 contracting to this, okay, then so this is going up, okay. We have a Q2, then there exists a Q2 such that Q2 contains Q1 and Q2 contracts to P2. So the given information is this chain here and something in S2 that maps on to P1. Then the chain goes up. That's what going up says. Okay. So now let's go back. What is the situation that we have here? We have R over A integral. Okay. Here is a prime which contracts to this prime here, but here is a chain going down. Can we extend it to a chain going down here? Okay, so does there exist P? Let's just let's call this thing PL. Okay, PL minus 1, PL minus 2, so that this contracts to here, this is whatever here, and then so on. Okay, so this is going down. Okay. So this is, if we can prove this, then we will know that this has length larger than this, larger than or equal to this, and hence we will know that height of P is greater than the height of this. Okay. So this is what we need. So what we need is step 2 is called going down theorem. Okay. So let me just, so I will not state the theorem, it requires some hypothesis, etc. So let's let me okay. So what it says is, given a chain like this, and a prime ideal here mapping to the first one, the topmost one, there is a chain going down mapping successively to the lower ones. Okay, so such a chain exists, and what we need to use in the theorem, so such a chain exists. Okay. Okay. So this is the going down theorem. Okay. So let's okay. So this is going down. Going down theorem for integral extensions. There are other going down theorems. Okay. And what one needs to use, in addition to the statement of going up theorem, one has to use the fact that this thing here is integrally closed in its field of fractions. So that is necessary. I mean, that's part of the hypothesis. It would fail if you don't assume that the smaller ring is integrally closed in its field of fractions. Okay, so using that hypothesis, one has a going down theorem, and it says precisely such a chain exists. Therefore, height of P is greater than the height of this. Okay, and therefore it will give an inequality in the other direction, and that would prove the statement. Okay. I mean, that is proof for this for P. Okay. So this is the proof. So this will prove the statement. Okay. So what I gave is just a very rough sketch of this argument. We need to prove the stronger version of Nature normalization lemma. We need to prove the growing down theorem. And after we prove these two statements, one can put the argument together, one can fill in the details of this argument and conclude that every chain of primes, every saturated chain of primes in spec of the polynomial ring over a field has same length equal to dimension of R. Okay. Yeah. Okay. So this is a general theorem that applies not just to polynomial rings or algebras over fields. It's sort of in the same generality as the going up theorem. You need some extra hypothesis on the ring, but it's generally in that context. Okay. While the Nature normalization lemma is about algebras that are finitely generated over fields. Okay, so that's just a brief. Okay, because this is a so this is sorry, I mentioned that I will discuss some condition that's equivalent to this. Okay, that every saturated chain of primes has the same length. One condition we saw in the proof, which is this: height of P plus dimension R mod P equals n for all P primes. Okay, for all primes P, it is equal, that we saw. Another condition that's equivalent to this is the following, which is that given P inside Q prime ideals of K adjoint n variables, okay, K field, okay, every saturated chain from P to Q has the same length. Okay, which is equal to height of Q mod P. In the quotient ring R mod P, the height of Q in there. Okay. So this is another way of saying this same property of polynomial rings, and often this nice property about spectrum, that all chains between 2 points have the same length, is sometimes useful in various problems. Okay. Although in this course we are unlikely to have to use it, but it is an important geometric property of some Noetherian rings. Okay. Not all Noetherian rings have this property. Okay. So now I want to change topic a little bit and want to look at graded rings. I mean, mostly we want to understand and use modules over, so we want to understand. So this is, okay. We are not discussing polynomial rings over fields or generality of Noetherian rings anymore. We will concentrate finitely generated graded ideals, I mean modules, over K x1 through xn. And when we say graded, we have to actually say what is the grading of the ring in which degree of xi equals 1 for all I. Okay. We can develop this slightly more generally without assuming this. We can just assume that all of them are positive, but it's sort of it complicates the arguments, but yeah, ultimately even in that case, although we won't discuss it, many of the problems can be reduced to some other ring in which this is true. All the generators have the same degree, so I think as a first round of understanding, this is good. Okay. So in order to do this, we will right now discuss a little bit more general. So we will assume that for now, initially, okay, we will assume that R is a Z-graded ring. Okay, so the polynomial ring with that grading I specified is actually non-negatively graded, k in degree 0 and all polynomials of positive degree in positive degree, the natural degree notion of degree of a polynomial. But we may have to work occasionally with Z-graded rings just in the initial setup. So we will allow the initial parts we will develop in this generality. Okay? And even over this, we will have to assume that M is Z-graded. Okay? Just for now. Okay? So this means that R is a direct sum of Ri, I is in Z. Okay? Each Ri. Okay, so this is okay. R0, it decomposes like this, with Ri, Rj is inside Ri plus j. So this says that R0 is a ring, subring of R. Each Ri is a module over R0. This is not the first time we are seeing graded rings, but just to remind ourselves what we are assuming. Yeah, this is not the general. This is not the first time we are seeing this, but just to remind ourselves where we are standing. Okay. So now, proposition. Let M be a graded module R module. Okay. Then and Y M inside M, a homogeneous element. Okay. In other words, M belongs to one of the samans. Okay. So similarly, similar to this, there is M also decomposes, okay, and Ri times Mj is inside Mi plus j. Okay. Homogeneous means it is in one of these pieces. Okay. Yeah. So let a homogeneous element. Then the annihilator of M in R is homogeneous. Is a homogeneous ideal or a graded ideal of so this is proof. So let F inside R be in the annihilator of M. Okay. The point about a graded ring is that it can be written uniquely as F equals sum of some Fi, I in some finite range. So let's call it N1 to N2, N1 less than or equal to N2. Okay, uniquely as this. So this implies that sum of Fi M is 0, but each of these live in different degrees. The only way it can be 0 is that individually they are all 0. Okay, and if for every f in this, its homogeneous parts are in the ideal, then this would imply that we can do this for every generator, and each generator itself breaks up into its homogeneous parts. So we can actually get a generating set based out of homogeneous parts. So in other words, annihilator of m, annihilator of x of m, little m is homogeneous. Okay, so we do this argument for every take a generating set and then do this for every generator, and then we would get this. Okay, so an immediate corollary is that associated primes of M. So let's assume that R Noetherian, and R Noetherian means M has an associated prime. Associated primes of M are homogeneous ideals. Okay, that is this requires a little bit of working, but if there is an annihilator of some element, we can actually break it up into annihilator of homogeneous elements, and then yeah, maybe I should not have said it's an immediate corollary. One can use the same argument to prove the statement. Okay, and another corollary is the following, which is that M. So now let's assume M has M is finitely generated in addition to R being Noetherian. Then we saw that then M has a prime filtration. Okay, M, let's call this thing ML, contains ML plus minus 1, contains ML minus 2, and so on. Some M1 contains M0, which is 0. Okay, prime filtration by graded submodules such that Mi mod Mi minus 1. Now this is a graded module, is isomorphic to R mod Pi for some graded prime ideal Pi. Okay, so we will, this is slightly loose, and we will see that a little later. We will not refine this statement. All that at this point I want to emphasize is that we could choose the submodules to be graded, and so that this is true. Okay, this is not what is called a graded isomorphism. It's just an isomorphism as modules, not isomorphism as graded modules, which we will discuss just a little later. Okay, so so we'll end this lecture now, and in the next lecture we'll continue discussing more about the first topic that we will want to discuss is the dimension theory of graded rings, which we will build from the dimension theory of Noetherian local rings. What exactly do chains of primes in support of M look like, and then we'll use that, and then we'll sort of specialize ourselves into the polynomial ring over a field situation.